Hi, my name is Satheesh. I'm pursuing my master's from Liverpool John Moore University. I would like to thank you for providing this opportunity to talk about my thesis. My thesis is based on disk failure prediction using bidirectional LSTM in heterogeneous environments. So let's begin. The demand for data storage is ever increasing. Social media, OTT platforms, big data analytics have increased the demand for storage. Companies are making business critical decisions based on data, and to make good quality decisions, they need huge amount of data. To store huge amount of data, they require storage solutions, backups. Companies need to store backups of critical data they cannot afford to lose. That again increases the demand for storage. Data centers provide these companies looking out for storage solutions a good model wherein they can pay for as much as storage they use. To maintain a market edge over others and to maintain a healthy competition, data centers have to optimize their costs and they have to be very careful with their inventory management. Data centers use hard disks for storage. Hard disks typically last for 3 to 4 years on an average. They account for more than three-fourths of the component failures in a data center. So that makes prediction of hard disk failures an important problem. To predict hard disk failures, we need some sort of data, right? That comes from SMART attributes. SMART stands for self-monitoring, analysis, and reporting technology. Basically, a hard drive is able to report its status to the host system, and there are about 255 attributes, but not all of them are used, and there is a lack of standardization among manufacturers regarding smart attributes. And then let's talk about homogeneous population of disks and heterogeneous population of disks. Basically, by homogeneous populations of disks, we mean disks of same make and same model. And in heterogeneous populations of disks, we are talking about combination of uh, disks from variety of uh, vendors, different make and model. Let's talk about our aim and objective of this study. Our goals are to identify generic parameters based on smart attributes for heterogeneous population of disks. We are going to implement a bidirectional LSTM model on top of these generic attributes that we have identified. We'll also compare our model with a model based on LSTM, and then we'll compare the performance of our model when applied on homogeneous population of tests. Before we talk about how we approached the problem, let's talk about literature review. The field of hard disk failure prediction is widely studied as it's an important problem to solve, both in industry and academia. From our study, we found that there has been variety of approaches to solve this hard disk failure prediction problem. Some have used decision trees, some have used ensemble learning, some have used long short-term memory. Uh, some did not treat the problem as a binary classification problem at all. They treated it as a multi-class classification problem wherein they categorize the disk's health into multiple categories based on remaining useful life. So a certain category, if the prediction falls under certain category, a disk may have a longer remaining useful life, and if it falls in certain other category, it may have very less remaining useful life, or it's basically about to fail. So to predict, most of these models have used smart data. Smart stands for self-analysis, self-monitoring, analysis, and reporting technology. That's basically the attributes that signal the health of an hard disk. Sector reallocation error, unreadable error counts, and attributes similar to these. One of the problems we noticed is lack of standardization among vendors about this smart data. Also, most studies focus on homogeneous population risk. So from the data set, they only pick um, a certain make and model, primarily because vendors don't agree on on the smart attributes, and lack of standardization. An effective hard disk failure prediction model should have a very high failure detection rate, that's FDR, and a low FAR, that's false alarm rate. There has been studies, as we spoke in the last slide, there has been multiple approaches. LSTM has been used. There are other metrics on based on which we can predict failure of hard disk. That's one of the other studies focused on migration rate and mismigration rate. Migration rate is basically how much data need to be moved around because a disk was predicted to fail, and how much mismigration had done, wherein a false prediction caused data to be moved around, but the disk was did not fail. There have been other approaches wherein uh, they combine multiple algorithms to increase the prediction accuracy. So in one of the studies, we saw that they have used XGBoost, LSTM, and Ensemble learning together to increase the prediction accuracy. There have been also studies on update strategies. So most of the studies considered this smart data set as a static value, and then made their predictions and models based on that. But there have been studies on how to update these static models, basically by giving continuous inputs in order to solve the aging dataset problem. Let's talk about the methodology we have used in our study. To make a prediction, we need to deal with a large amount of data. We sourced our data from Backblaze dataset. The dataset is very popular um, because it captures daily snapshot of a data center that's in use, and it also fits our requirements as it contains multiple makes and models and uh, details about uh, various smart parameters, which is very useful for our study. In our study, we'll analyze the data set, we'll understand the data, we'll pre-process, we'll try to uh, use certain sampling techniques, and then we'll evaluate our model, compare our model with other existing models. We'll also study um, uh, our model's performance on homogeneous set of disks just for the comparison purpose. Let's discuss this system requirements, our implementation and results of our study. We used a Linode VM because of high-end requirements. We need we used 16 core CPU, 300 gigs of RAM. We set up Jupyter Notebook on this remote server. We also used pandas to pre-process our data and analyze the data set. We used TensorFlow and Keras to implement our model. As far as the dataset is considered, we use the Backblaze dataset, and this dataset is limited to the period of Q1 2021, primarily due to resource constraints. As seen in the image, the dataset had a variety of make and model of disks. After pre-processing, we took a value count of disks by model. As seen in the slide, Toshiba model had the highest count with just over 2 million records. We used this disks, um, this particular disk for our homogeneous disk population later in our study. During the analysis of this dataset, we encountered multiple issues. Let's discuss them. So, when we analyzed the dataset, we found out that the number of healthy disks vastly outnumber the instances where we had failed disks. So this creates the class imbalance problem. Any model we create on such dataset will be skewed towards the majority data class. In order to solve that problem, we there are multiple techniques. SMOT is one, basically synthetically creating records. We used upsampling. Uh, so we basically replicate a minority class in order to match uh, the count of majority class. We also face the multicollinearity problem, as in many smart attributes were very highly correlated. So we did some analysis and then selected certain attributes which were best fit. We used RFE, recursive feature elimination, for selection of such attributes. We also studied the LSTM, long short term memory, versus bidirectional LSTM and the performance of each algorithm. Bidirectional LSTM, while it takes more time to train, it has more situational awareness about the dataset, and at any point of time it has more understanding of the dataset when compared to classic LSTM. After selection of certain attributes and building our model based on that, we saw that bidirectional LSTM performed the best over all other models, but it only gave a marginal improvement over LSTM, and we believe that's because of the size of the dataset, the and that's with a reason. We also trained the model with various sizes of dataset. So we took 1 day, 10 days, and 30 days and 100 days respectively, and we saw the margin of difference, the improvement bidirectional LSTM provides over LSTM increase uh, gradually. We plotted the accuracy of both training dataset and test dataset. Um, as we can see in the image, it increases in initially, but after certain epochs it remains consistent. Let's talk about the conclusions we made and the future recommendations we have. As we saw earlier, our model achieved 80.74% of accuracy. We found from our study that the margin of improvement over LSTM is less, but it increases with the dataset size. Uh, Bidirectional LSTM also takes more time for training when compared to classic LSTM. Uh, let's talk about the future recommendations we have. We believe additional data sources can be used to predict hard disk drive failures better. Most of the studies use smart data as their primary source. We believe additional data such as performance counters and error logs from the host system can also explain hard disk failure, which can be used as an indication of impending failure. Another avenue that we think can be explored is to regroup disks by the make and model, and then identifying smart attributes specific to those make and model, and then building a larger model which can increase the prediction accuracy. The third recommendation we have is push for standardization uh, in smart attributes among the manufacturers and vendors. This will ensure that we have normalized data and increase the effectiveness of prediction in hard disk uh, failures. I would like to thank you for the opportunity for presenting my thesis. Thank you. Have a good day.